This is MAT 221. This is Mrs. Johnson. We're in section 2.5 talking about limits to infinity and infinite limits. We just finished up this example and we saw that as we approach zero from both the left and the right, this hyperbolic function tended to positive and negative infinity. We also see that the limit does not exist here because we have two different targets, but this also gives us the idea that there's a vertical asymptote at x equals 0. Because the limit is approaching infinity or negative infinity as x approaches 0. Which brings us to the definition of a vertical asymptote. We say a line x equals a, remember our vertical line has the equation x equals some number, is a vertical asymptote of a graph of a function y equals f of x. If either the limit as x approaches a from the positive side tends to positive or negative infinity, or the limit as x approaches a from the negative side of the function tends toward positive or negative infinity. This is the official definition of what a vertical asymptote is. Now, a function can have many vertical asymptotes. It can only have at most two horizontal asymptotes, but it can have many vertical asymptotes depending on the function. Vertical asymptotes often occur when the denominator of the function is equal to 0, but not always. Notice I say often because it doesn't always happen that way, but with most rational functions it will. But remember, sometimes we could have where the denominator is equal to 0, but there's a hole in the function and there's not a vertical asymptote. And then there's other ideas too that we can go through. So if I said to you, find the vertical asymptotes of this power function 1 over x squared, which is that curtain function. As x approaches positive infinity, as x approaches 0 from the positive side, if I put in smaller and smaller numbers like 1/10, 1/1,000,000th, right? This is tending toward positive infinity. And if I put in negative values, because of the square, this also is going to be a positive value, so that will also tend toward positive infinity. Notice the denominator is always positive in both cases, so both limits will be the same here. So the limit as x approaches 0 of 1 over x squared is equal to infinity. Now notice I have the same targeting value. Now technically, there's no targeting exact value. There's no exact y value that this is targeting, but we say that from both sides, we're tending toward infinity, or we say that the function increases without bound, but both targets are both targeting this increasing without bound concept. So we say the limit as x approaches 0 actually tends toward that target value of infinity. So the line y equals 0 is again a vertical asymptote for this function. Here's the actual function. We could say that the limit does not exist, or we could say that the function tends toward infinity. Both actually are correct answers. However, we can indicate the behavior as x approaches 0 by saying that the curve is tending toward infinity. But technically, the limit doesn't target an exact y value anywhere on this function. As x approaches 0 from the left, as x approaches 0 from the right, this curve is increasing without bound, tending toward infinity in both cases. So we say that the limit as x approaches 0 of 1 over x squared equals infinity. Technically, we could say it does not exist because there's no exact y value, but this is telling us that there's a vertical asymptote, that there's vertical discontinuity or infinite discontinuity, there's a vertical asymptote, and that the function tends toward an output of infinity. Now, the limit as x approaches a given number from both sides can look something like this, where we tend both sides in the same direction. We say tending toward infinity. We say the limit as x approaches a is infinity, or f of x becomes infinite as x approaches a, or we say f of x increases without bound as x approaches a. We technically could say that the limit does not exist. However, we usually say because there's no exact y value that is being targeted. However, because the tendency of the function is tending to increase without bound, we usually bring in the concept of infinity. We could do something like this, where the limit as x approaches a from both the left and the right, notice we see in this case, is tending toward negative infinity. So here's some illustrations of different ways that we could approach a vertical asymptote. We could come to a vertical asymptote from the left and approach infinity. We can approach a vertical asymptote from the right and approach infinity. Or we could approach a vertical asymptote from the left and have the function approach negative infinity. Or we could approach the vertical asymptote at x equals a from the right, and the function will tend toward negative infinity. So you can see the red line is the vertical asymptote, and the blue would be the function. So let's look at this function from both the left and the right, as x approaches 3 from the left and as x approaches 3 from the right. Now it's the same function. This is a rational function. We know that the function is not defined at x equals 3. Matter of fact, there's going to be a vertical asymptote as x approaches 3. So let's look from both sides. As x approaches 3 from the left, notice that my curve is approaching negative infinity as x approaches 3 from the left. As x approaches 3 from the right, my curve is approaching positive infinity. So these are considered one-sided limits because of the plus or minus sign next to the 3 there. Now the other way we could do this is we could look at the function and say, let's look at a value really, if we didn't have, say we didn't have the graph. Let's look at a number close to 3 from the positive side. So close to 3, but a little bit bigger than 3. So let's say 4. If I said 4, the numerator would be positive, the denominator would be positive. If I said 3.5, the numerator would be positive, the denominator would be positive. If I said 3.1, the numerator would be positive, the denominator would be positive. So notice I'm getting a positive over a positive, and therefore as I'm approaching 3 from the positive side, notice my curve is tending toward positive infinity. So let's go back to this one. Let's approach 3 from the negative side. So let's put in 2. The numerator would be positive, the denominator would be negative, and a positive over a negative would be a negative number. If I put in another number closer to 3 from the negative side, like 2.5, the numerator would be positive, the denominator would be negative, so I'd have a positive over a negative, again a negative number. If I put in 2.99, positive, negative, so I'd get, notice, I can do a little bit of work here just mentally, and I could figure out that as I approach 3 from the negative side, my curve is tending to negative infinity. I knew that there was going to be infinite discontinuity at x equals 3. Then I figured out how it actually is behaving. So we have a vertical asymptote at x equals 3. So let's look at something like this. This is something you might see on WebAssign or see on a test or quiz also. Find the infinite limits, the limits at infinity, and the asymptotes for the function f of x, whose graph is shown. So let's find the infinite limits, the limits at infinity, and as asymptotes for this function whose graph is shown. So if we look for limits at infinity, that's as x approaches positive and negative infinity. So infinite limits are those limits where the answer is infinity. So if we look at this graph, we look, where's the curve have vertical asymptotes? Because here we say as x approaches -1 from both the left and the right, you can see that the curve is approaching positive infinity. And then over here at x equals 2 is another vertical asymptote. So the limit would also equal infinity there. So those would be our infinite limits. So let's write them. The limit as x approaches -1 from the negative side, as x approaches -1 from the negative side, is equal to positive infinity. As x approaches -1 from the positive side, so as x approaches -1 from the positive side, also approaches infinity. These two, again, are the same tendency. So we say the limit as x approaches -1 tends toward infinity. Now what about at x equals 2? Well, if I approach x equals 2 from the negative side, I know that my curve is tending toward negative infinity. The limit as x approaches from the positive side is tending toward positive infinity. These do not agree with each other, so the limit as x approaches 2 from both sides does not exist. All right, what about the limits to infinity, or the limits at infinity? So let's look at the limit as x approaches infinity. So as x gets really, really large, so as x goes this way, my value of my output of my function looks like it's leveling off to a value of positive 4. Let's look at the other tail. As x approaches negative infinity, so as x goes this way toward negative infinity, the value of the function looks like it's coming down and leveling off at y equals 2. So we have a horizontal asymptote of y equals 4, or f of x equals 4, and we have a horizontal asymptote of f of x equals 2, or y equals 2. We have a vertical asymptote at x equals -1, and we have a vertical asymptote at x equals 2. Now I didn't draw them there, but I definitely could have drawn those asymptotes in this function. All right, just a little bit of notation. The notation, the limit as x approaches infinity of f of x equals infinity, is used to indicate that the values of f of x become large as x becomes large. Similar meanings are attached to these symbols. The limit as x approaches negative infinity of the function, and so forth, right, as you go through. So these can be difficult sometimes to understand those concepts. Here's some examples. The limit as x approaches infinity of e to the x. So as x approaches infinity, e to the x is tending toward positive infinity. Notice e to the x also has a left tail behavior as x approaches negative infinity. This actually has a horizontal asymptote of y equals 0, or a target value of 0. The limit of x cubed as x approaches infinity tends toward infinity. The limit as x approaches x cubed toward negative infinity also tends toward negative infinity. Finding an infinite limit at infinity. Let's try another example here. The limit as x approaches infinity of x squared minus x. It would be wrong to write this limit like this. The limit laws do not apply when we're talking to infinity. The limit of the difference of two functions is not equal to the difference of the limits when you're tending to infinity. This is actually giving us infinity over infinity minus infinity, which the limit laws cannot be applied to infinity because infinity is not a number. And infinity minus infinity is actually what's called an indeterminate form in mathematics. We'll look at this later in the course when we get into L'Hopital's rule. We can do this though. We can write that the limit is equal to, we can factor it out and look like this, right? Both x and x minus 1 become arbitrarily large. This also tends to infinity. All right, so that finishes up section 2.5. Again, look for some videos on the worksheets that we have that you were given in class and that are on Blackboard to practice some more of these skills. Also work on WebAssign for sections 2.4 and 2.5. Have a great day.